Transformers.js brings state-of-the-art machine learning to JavaScript. You can think of it as a library for running AI models locally in the browser through a single high-level API that handles model loading, preprocessing, inference, and postprocessing. Hi, I'm Nico, and in this video I want to give you the mental model for how Transformers.js works, models, tensors, ONNX, quantization, pipelines, and what actually happens under the hood. Before we dive deeper, here is what this looks like in practice. First, text generation. Transformers.js lets you run LLMs directly in the browser, from tiny sub-1B models to larger mixture of experts models like GPT-OSS20B. Second, automatic speech recognition. Drop in an audio clip and get a transcript. Third, background removal. Pass in an image and get a clean foreground cutout. Same JavaScript library, same high-level API style, 3 very different machine learning tasks. And those are only 3 out of 27 different tasks Transformers.js supports. Now, let's break down how this actually works. Let's start with the fundamentals behind Transformers.js machine learning. Most modern machine learning systems are built with artificial neural networks. At a high level, a neural network takes in one tensor and produces another. So what exactly is a tensor? It is just numbers organized by shape. It could be a scalar, which is just a number or a zero-dimensional tensor, a vector, which is an array of numbers or a 1D tensor, a matrix, which is an array of arrays of numbers or a 2D tensor, and then higher dimensional versions of the same idea. But in all cases, it is just numbers. And that is important because everything is processed using mathematical operations. If we look at a neural network, we have often an input layer, one or more hidden layers, and an output layer. The connections between neurons each have a value attached to them, and that value is called a weight. Each neuron combines its inputs using those weights, usually adds a bias, applies an activation function, and passes the result forward. During training, the model adjusts those weights and biases to reduce errors and improve its predictions. Yes, this example is super tiny, but in practice, we are talking about millions to trillions of those connections per network. So in short, to run a neural network, we need three things: the architecture, the model graph that describes the layers and operations, the weights, and a runtime that executes the math. So the next question is, how do we package a model and run it across different environments? There are many frameworks and standards that package those building blocks in different ways. Transformers.js uses ONNX, which stands for Open Neural Network Exchange. ONNX stores a model as a computation graph plus trained weights, usually in a .onnx file and sometimes with external ONNX data files for very large models. The key idea is that the model format is separate from the runtime. In other words, ONNX describes what to compute and the runtime decides how to compute it on the current hardware. That separation is a big win for JavaScript. The same model can run with different execution providers depending on the device, like WebGPU or WASM in the browser, or CUDA and DML in native environments. Before we move on, there is one more concept that matters a lot for web inference: quantization. Quantization means storing and running model weights with lower numerical precision, for example FP16, Q4, or even 2-bit or 1-bit instead of full FP32. To make that concrete, with 32-bit precision, each value gets 32 bits to represent a number. With 4-bit precision, each value gets only 4 bits. So we remap numbers into a much smaller set of possible values. That's why quantized models are more compact, but also less precise. The benefit is usually smaller model files, faster downloads, lower memory usage, and often faster inference. The trade-off is that you can lose accuracy. so the best choice depends on your task and quality requirements. In Transformers.js, you can often choose quantized model variants with D-type, so you can balance quality, speed, and memory without changing the rest of your application flow. Okay, but if inference runs in ONNX runtime, why do we need Transformers.js? Transformers.js basically handles three things for you. First, Transformers.js figures out which files a model needs, downloads them, and caches them so you do not have to fetch everything again on the next run. In the browser, this uses the cache API. In server-side environments, it uses file-based caching. And if you already have your own caching layer, you can plug in a custom cache with Transformers.js. That sounds simple, but it matters because different tasks can require different assets. Model weights, tokenizer files, processor configs, and sometimes multiple model parts. Second, it converts your raw input into tensors in the exact format the model expects. And that input can vary a lot by task. Plain text for sentiment analysis, text pairs for question answering, images for classification or detection, audio waveforms for speech tasks, or even combinations for multimodal models. Third, it turns raw input tensors back into something useful for your app. Depending on the task, that might be class labels with confidence scores, generated text, translated text, transcriptions, embeddings, or bounding boxes and masks. So even though ONNX runtime executes the math, Transformers.js gives you a consistent high-level interface across many different input and output types. The easiest way to use Transformers.js is through the pipeline API. Based on a given task ID, it handles a lot of preprocessing and postprocessing behind the scenes. So what is a task in this context? A task is basically a contract. It defines the kind of input you provide and the kind of output you get back. For example, depth estimation expects an image as input, while feature extraction expects text. So even before inference starts, the preprocessing path is different. Image to image tensor for depth estimation, and text to tokenized tensors for feature extraction. The outputs are different as well. Depth estimation returns a depth map where each pixel estimates how far that part of the scene is from the camera. Feature extraction returns text embeddings, which are numerical representations you can use for things like semantic search or clustering. That is the key idea of task in Transformers.js. One consistent API, but different input-output contracts depending on what you want to build. To make this concrete, let me show you the task landscape in Transformers.js grouped by category. We have natural language processing, computer vision, audio, and multimodal tasks. Each of these categories contains task IDs you can pass directly into pipeline, like summarization, object detection, automatic speech recognition, or image to text, and so on and so forth. Some tasks also have aliases like sentiment analysis for text classification. At code level, you create a pipeline like this. You can think of pipeline as an async factory that gives you a task-specific function, a pipe. Task ID selects the pipeline contract. Model ID tells Transformers.js which model to load, usually by referencing a repository on the Hugging Face hub, but it can also point to a local model depending on your environment setup. If you skip it, Transformers.js picks a default model for that task. And then you have options where three settings are especially important in practice. Progress callback lets you track model download and loading progress, which is very useful for UI feedback. Device lets you choose where inference runs, for example, WebGPU or WASM in the browser, depending on availability and performance. Since version 4, we recommend WebGPU also for server-side JavaScript runtimes. D-type controls numerical precision such as FP32, FP16, or quantized formats like Q4 or Q4F16, so you can balance quality, speed, and memory use. So pipeline creates and returns a pipeline object first, then you call that pipeline with your actual input and task-specific options. If you need deeper infra-level control, Transformers.js also exposes a global env object for model routing, caching, and runtime behavior. I am skipping this in this intro, but you can find details in the Transformers.js docs. So far, we looked at the interface. Now let's trace what happens internally when you call it. Let's look inside one concrete pipeline, text generation, which is used to run large language models. Imagine your input as an array of chat messages. First, Transformers.js applies the tokenizer and chat template. So the messages and generation settings become one structured prompt in the format the model expects. Then that prompt is tokenized into token IDs, and those IDs are converted into the model input tensors. Inside the model, token IDs are mapped to embeddings. From there, the model runs inference over many layers and outputs scores for many possible next tokens. Then decoding decides which token to take next. With greedy decoding, it picks the highest score token. With sampling enabled, it samples from a probability distribution shaped by settings like temperature. Higher temperature usually gives more variety, lower temperature is more deterministic. That new token is appended to the running sequence, and the process repeats. Run inference, predict next token, append, and continue. This generation loop stops when the model emits a stop token or when it reaches the configured maximum number of tokens. At the end, Transformers.js handles postprocessing. It decodes token IDs back to readable text and returns the final response in a clean output format. So even though it looks like one simple pipeline call, there's a full tokenizer, tensor, model decoding loop happening under the hood. Now compare that with depth estimation, which is much more of a single pass vision pipeline. You start with an image input, Transformers.js loads and prepares it, then applies the image processor steps like resize and normalization so it matches the model requirements. That processed image is converted into an image tensor and sends through the model in one forward pass. The model returns a depth prediction tensor, where values represent relative distance across the scene. Then Transformers.js post-processes that tensor into a usable output, typically both the raw depth tensor and a depth map image you can render on screen. To sum it up, different tasks execute differently under the hood, but the developer experience stays consistent. And that is the core strength of Transformers.js. It abstracts away the implementation details of around 200 model architectures across 27 different tasks and gives you one unified API to run them. In this intro, we covered the core ML concepts, why ONNX matters, how quantization changes the speed versus quality trade-off, and what the core library handles for you around model loading, preprocessing, and postprocessing. So in short, if you can call an async JavaScript function, you can ship local ML features in web apps with this. Thanks for watching, and I hope this gave you a clear mental model for how Transformers.js works.